myself Dr. Pruthviraj B S. In today's session we shall see how to analyze a continuous beam with the help of Kanis method where one support is subjected for sinking. So for that I have considered a simple problem over here where span AB is having a span of 3 meters and carrying an UDL of 40 kilonewton per meter, and span BC is having an central concentrated load of 100 kilonewton, and span CD is carrying a UDL of 50 kilonewton per meter, and the span over here is 3 meters. So they have given the support B sinks by 2.5 millimeters and the value of EI they have given, which is 7000 kilonewton meter square. So from the previous classes we have learned the first step in the Kanis method is to calculate the fixed end moments. To calculate the fixed end moments. So if I consider this span over here, it is for span AB. See, in the question they have given here that the support B sinks by 2.5 millimeter. That means the effect of sinking we have to consider while we are calculating the fixed end moment over here itself. So if I consider the span AB over here, this is span AB, where the support B is subjected to a sinking they have given, which is 2.5 millimeters. So if I convert this in terms of meter, which will be equal to 0.0025 meters, and the sign convention here is the negative. So this support which is sinking by 2.5 millimeter, this effect also we need to consider while we are calculating the fixed end moment over in this state itself. So the fixed end moment from A to B, since it is carrying an UDL of 40 kilonewton per meter, the formula we know for fixed end moment, which is WL square upon 12. Since we are coming from left to right, the sign convention is negative over here. Also we need to consider the effect of sinking over here. Since it is negative here, the formula is 6 EI delta upon L square. So here it will be minus 6 EI delta upon L square. So now taking the values of this one, W we know which is 40. So minus 40 into the span over here, length is 3 meters. So 3 square upon 12 minus 6 into EI value they have given, which is 7000 kilonewton meter square, into delta, which is in terms of meter we have converted into 0.0025 upon L square, which is the span over here for span AB, which is 3 square. So calculating this we get a value of, so this we get a value of minus 30, and this value we get as 11.67. So the fixed end moment from A to B, the value will be equal to minus 41.67 kilonewton meters. Next, calculating the fixed end moment from B to A. So now we are coming from right to left. The formula remains same, which is WL square upon 12. Only the sign changes, that is W plus WL square upon 12 minus the effect of sinking over here. The formula is 6 EI delta upon L square. So minus 6 EI delta upon L square. So here we have calculated the value, which is minus 30. So here it will be same, but the sign changes, which will be equal to plus 30 minus 11.67. So fixed moment from B to A will be equal to 18.33 kilonewton meters. Same way calculating the fixed end moment for span BC over here. For span BC, fixed moment from B to C will be equal to, since it is carrying a central concentrated load, we know the formula WL upon 8. Since we are coming now from left to right, the sign convention is negative over here. See here, the effect of sinking from A to B we have considered in the negative direction. Similarly, if you consider for span BC over here, this is C and this is B. Now the effect of sinking here. So this B is having a sinking of 0.0025 meters they have given. So since here the sign convention is positive, so 6 EI delta upon L square, this effect of sinking needs to be considered in the positive direction. So it will be plus 6 EI delta upon L square. So the value of W they have given, which is 100 kilonewton. So minus 100 into the span here, which is 2 meters upon 8, plus 6 into the value of EI they have provided here, that is 7000, into delta is the sinking 0.0025 meters. So the fixed end moment from B to C will be equal to, we are having a value, this value will be equal to minus 25 plus this value over the L, this is the span over here, over L square. So this value will be equal to 26.25. So the fixed end moment from B to C will be equal to plus 1.25 kilonewton meters. Now calculating the fixed end moment for span C to BC only, that is fixed moment from C to B. See here. So now the fixed end moment from C to B will be equal to, the formula remains same, since we are coming from right to left here, the sign only changes, which is positive plus WL upon 8 plus 6 EI delta upon L square. So W here is given, which is 100, the span here is 2 meters for span BC upon 8 plus 6 into EA value they have provided 7000 into delta value is 0.0025 meters upon the total span here is 2 square. So the fixed end moment from C to B will be equal to, this value is equal to 25 plus this value is equal to 26.25. So fixed end moment from C to B, which is equal to 51.25 kilonewton meters. So now calculating the fixed end moment for span CD. See here, for span CD, so fixed end moment from C to D, which will be equal to, see here they have given in the question that this effect of sinking is only at the support B, so the effect of sinking is not considered for the span CD over here, because see, if a support is sinking over here like this about 2.5 millimeters, so the effect of sinking is only for the span AB and for span BC and not for the span CD over here. So we need not consider the effect of sinking for the span CD. So we directly consider the formula which is given for the fixed end moment. Since it is carrying an UDL, the formula will be, we are coming from left to right, which is minus WL square upon 12. So which will be equal to, the value of W here is minus 50 and the span is 3 meters. So 3 square upon 12. So fixed end moment from C to D, which will be equal to minus 37.5 kilonewton meters. Same way, fixed moment from D to C coming from right to left. The formula remains same, only the sign changes. So which will be equal to plus WL square upon 12. So W here is plus 50. The span is 3 meters upon 12. So fixed end moment from D to C will be equal to plus 37.5 kilonewton meters. So the next step will be here to calculate the stiffness, which is represented by K, and rotation factor, which is represented by U. So for that, let us consider a table over here. First we will consider the joint and member for that particular joint, and then for that particular member we shall calculate the stiffness, and then we will consider the total stiffness, which is given by summation K, and we will calculate the rotation factor, which is given by U, is equal to minus half into K upon sigma K. See, if you observe here, we are having two intermediate supports, and those intermediate supports can be treated as the joints over here. So joint B, we are having two members, that is from B to A and from B to C. So B to A and B to C. So now if we see, if you want to find out the stiffness, we have to observe the far end conditions. So since here B is the near end and A is the far end, and since A is a fixed support over here, the stiffness will be equal to I upon L. So I upon the span here is 3 meters. Next for BC, if you see, B is the near end and C is the far end. Since C is an intermediate support over here, even the intermediate support also we are considering it as an fixed end. So the stiffness will be equal to I upon L. I upon the value of the total length here is 2 meters. So if we just put the value over here, and if we take the total stiffness, which will be equal to 0.83 I. So here next, considering the joint C. So C is connected from C to B and C to D. So we are having two members here, which is from C to B and C to D. So if we come for the member CB here, C is the near end and B is the far end. Since B is an intermediate support here, it is also considered as a fixed support. So the stiffness will be equal to I upon L, which is I over 2. And for span CD, since C is the near end and D is the far end, and the far end is switched over here, the stiffness will be equal to I upon L. So I upon the total span here is 3 meters. So taking this value and adding, we are getting 0.83 I. So now if you want to calculate the rotation factor for each members here, just applying the values whatever we have got here, which is K I by 3 and sigma K here we have got 0.83 for member BA. The value will be minus 0.20, and for BC it is minus 0.30, and for CB the value over here is minus 0.30, and for CD the value of rotation factor is minus 0.20. We have to see that the total summation of this should be equal to 1. So the next step will be to calculate the rotation contributions through the iteration process. So for that we will consider a table which is also called as a Kanis table. And this Kanis table, what we have done here is we have replaced the intermediate support with the help of the boxes, because the rotation contribution is only calculated for the intermediate supports and not for the end supports. In this table we will represent the fixed end moment whatever we have got in the step 1. Also we will calculate the summation of the fixed end moment over here in this box, and also we shall represent the rotation factor whatever we have got for the member, that is BA, BC, CB and CD over here. So first representing the fixed end moment, that is from A to B. which we had got in the first step is from A to B it was minus 41.67. I will only consider the value over here and not the units. And from B to A it was plus 18.33, and from B to C it was plus 1.25, and from C to B it was plus 51.25, and from C to D it is minus 37.5, from D to C it is plus 37.5. So in this box we have to take the summation about this point here or this joint here, that is from D to A and from B to C. So what we have to do here, we have to take the summation of these two values, which will be equal to 19.58, and over here we have to take the summation of the fixed end moment from C to B and C to D, which will be equal to plus 13.75. And here in this place over here we need to represent the rotation factor whatever we have calculated in the second step. So here we are getting a value of minus 0.20, that is rotation factor from member B to A. Here it is minus 0.30, and from C to B it was minus 0.30, and from C to D it was minus 0.2. So now if you want to represent the, or if you want to calculate the rotation contributions over here, so let us consider this as M dash AB represented by M dash BA, and here M dash BC, here M dash CB, this is M dash CD, and here M dash DC. So we know that whenever we need to calculate the rotation contributions, that is represented by small m dash, we know the formula, that is rotation factor multiplied by the summation of fixed end moment plus summation of far end rotation contributions. So this is the formula we need to use whenever we are calculating the rotation contributions. So now, carrying out the iteration process, let us call it as cycle 1. So here what we will do here is, since we know that we are calculating the rotation contributions only for the intermediate supports and not for the end supports, we know that this value at the end supports will be equal to 0, that is M dash AB and M dash DC. So we need to calculate the rotation contributions only for the intermediate support. So for first cycle, if I calculate for M dash BA, we know the formula, which is U into summation of fixed end moment plus summation of far end rotation contributions. See here the far end rotation contribution for B here, if I see the far end rotation contribution is M dash AB, and here the far end rotation contribution becomes M dash CD. So these values I need to consider whenever I am calculating the iteration process. So for C, M dash BC and M dash DC is the far end rotation contributions. So M dash BA, the value of U we know here, which is minus 0.20 into summation of fixed end moment we have got here, which is 19.58 plus the summation of far end rotation contribution, here it is 0 plus M dash CB, the value we don't know, we need to calculate. So for the first cycle it is 0, which will be equal to minus 3.92 kilonewton meters. So this value we will consider over here, that is minus 3.92. So next, calculating the rotation contribution for B to C, this one M dash DC, the rotation factor here is minus 0.30, rest everything remains the same because the summation of fixed end moment over here is 0 and far end rotation contributions we don't know, we have to calculate. For the first cycle it is 0. So the value will be equal to minus 5.87 kilonewton meters. Next, for M dash CB, so U here is minus 0.30. So this value we will consider here, which is minus 5.87 into the summation of fixed end moment here, which is 13.75 plus summation of far and rotation contribution. Here it is 0. See, now if I consider the far and rotation contribution, here we have got a new iteration value. So we need to consider this value over here, which is minus 5.87, which will be equal to minus 1.576 kilonewton meters. So this value we need to consider here, which is minus 1.576. So m dash CD will be equal to minus 0.20, because this is the rotation factor here. Rest everything remains same, minus 5.87, which will be equal to minus 2.36 kilonewton meters. So this value will represent here, which is minus 2.36. So we have to go on carrying the iteration process until we get the same value over here. So what we will do here is, if we want to calculate for the second cycle, see here everything remains same, only the far end rotation contribution keeps on changing. So here if we take the far end rotation contribution here of this first 0, and the new iteration value whatever we have got here, which is minus 1.576, which will be equal to minus 3.60 kilonewton meter. So here minus 3.60. So here also it is same, plus 0 minus 1.576, which will be equal to minus 5.40 kilonewton meters. So here it is minus 5.40. So we can see here the values are changing. So here also everything remains same, only the rotation contributions about the far end changes. So now if we take the far end rotation contributions, which is 0 over here, and over here m dash BC we are having a new iteration value, so we will consider that one, which is minus 5.40, which will be equal to minus 1.67 kilonewton meters. So here plus 0 minus 5.40, which will be equal to minus 2.51 kilonewton meters. So here this value minus 1.67, here minus 2.51 kilonewton meters. So for the third cycle, since the values are still not equal over here, we will go for the third cycle. So everything remains same, only the far and rotation contributions changes. See here, the far and rotation contribution over here is what? The new iteration value is minus 1.67, here minus 1.67, which will be equal to minus 3.58 kilonewton meters. Here the value is minus 5.37 kilonewton meters. So this value we will represent over here, which is minus 3.58, and here minus 5.37. So here also, if we just change over here, we are getting this value over here, minus 5.37, here minus 5.37, where we are having a value of minus 1.67 kilonewton meters, here minus 1.67 kilonewton meters. So here minus 1.67, sorry, here it is minus 2.51, minus 2.51 kilonewton meters. So here it is minus 2.51. So if you observe over here, we are getting the same values over here. So if we go for the fourth cycle also, the values remains same here. So now we can say that this value over here in the third cycle, this value we can consider it as the final rotation contributions. So using this value we can calculate the final end moments. See here. So if we need to calculate the final end moments, so here this is minus 3.58. See here, the last step here, is step 4, will be to calculate the final end moments. So to calculate the final end moments, we know the formula which will be equal to fixed end moment from A to B plus 2 times the rotation contribution about the near end plus 1 times rotation contribution about the far end. So we have to consider the fixed end moment from A to B, which we have represented over here, that is minus 41.67 plus 2 times rotation contribution about the near end. About the near end it is 0 over here, and 1 time the rotation contribution about the far end. So m dash dA we have got a value which is minus 3.58 kilonewton meter. So the final end moment will be equal to the final end moment. Here we are getting a value of minus 45.25 kilonewton meters. So next, if you want to calculate moment from B to A, which is fixed moment from B to A plus 2 times rotation contribution about the near end plus 1 times rotation contribution about the far end. So here MFBA, which we have got the value over here, which is plus 18.33 plus 2 into the rotation contribution about the near end m dash BA value we have got here minus 3.58 plus this value is 0. So we are getting a final end moment from point B to A, which will be equal to plus 11.17 kilonewton meters. So similarly, same way if you go on calculating the other values, that is moment about point B to C, we are having the value of minus 11.17 kilonewton meters, and moment from C to B is plus 42.52 kilonewton meters, and from C to D we are having a value of minus 42.52 kilonewton meters, and moment from D to C will be equal to plus 34.90 kilonewton meters. So using these values we will just represent over here. For moment about AB we have got a value which is negative minus 45.25. Similarly over here, which is moment about BA, which is 11.17 kilonewton meters, and from B to C we have got a value which is negative minus 11.17. So see here, about B it is plus 11.17 and from B to C is minus 11.17. So the moments are equal and opposite in direction. That means the calculation is correct. So from C to B, here it is 42.52. 42.52. From C to B it is minus 42.52, and from D to C the value over here is 34.90. So using these values we can further calculate our support reactions and also the maximum bending moment. So similarly we shall see some more problems related to Kanis method in the next coming classes. Thank you.